All right, we're looking at horizontal projectiles. So we're going to start off with a cannon on top of a 42-meter tall cliff. So cannon. All right, and our cannon is going to shoot a ball with a velocity of 100 meters per second. And like all good cannon people, I don't know, what we want to do is figure out where the cannonball is going to land. Bombardiers? Okay. We're going to figure out where the ball is going to land. If we look at it, it takes that nice parabolic path that we see when we throw things, and that's part of what characterizes a projectile. Projectile is going to be any object that moves under the influence of only gravity. For examples like this, and for a first-year physics class, we're going to go ahead and ignore wind resistance and just say that it moves without wind resistance, knowing that it has an effect, and we might talk about that, but never in specifics and never with numbers. So a projectile is any object that moves under the influence of gravity. An airplane with jet engines pushing it has those pushing it, and that's not under the influence of gravity. So looking at this, we're going to take this problem and look at it from the front to where it's almost like the cannon is pointed directly at us, and we're going to look at it from the top to where we see the cannon on the edge of the cliff shooting. And we're going to see if there are any differences that we see there with those two things. Now, looking at it from the front, it's as if the velocity of the cannon is coming straight out at you. But really, all you would see is that ball dropping under the influence of gravity. And you really wouldn't see, far enough away, you wouldn't see the velocity. You'd see the cannonball getting bigger, but you wouldn't see the velocity. So from this view, it would appear that the thing starts off with a velocity of 0. And it would appear that it falls under the influence of gravity, which is still 9.8 meters per second squared down. And it would appear that it's falling, delta y, it's falling in y direction, 42 meters, also in the downward direction. That's the information that we can see just looking at it from the front. Or from the top's completely different. We wouldn't really see the cannonball fall down. We'd see it move this way. And really you'd see it move that way with a constant speed. Now that's hard to believe. You could stand on a table and have somebody roll a ball under your legs and watch it fall off the table. We'll have a video of that up shortly. But what we see is it moving with a constant velocity. So the acceleration there is 0. The velocity is equal to 100 meters per second. And we don't quite know how far it goes. In fact, that's what we're after. So what we're going to do is find the time somewhere. And what's nice is we can do that in the y direction because we know that the time in the y and the x is going to be the same. These two things are happening at once. So in the y direction, if we use our third kinematic equation, delta y equals v0t plus 1/2 at squared, that goes away because our initial velocity is 0. And delta y is equal to 1/2 at squared. We solve for t. Divide both sides by 2. Divide both sides by a. So we have the square root of 2 delta y over a is equal to t. If we plug in our numbers, the square root of 2 times 42 over 9.8, all of that being square rooted, gives me the time, which is 2.9 seconds. And if I want to know how far I go, delta x equals v0t plus 1/2 at squared. That goes away because the acceleration is 0, and my delta x is just my initial velocity, 100 meters per second, times my time, 2.9 seconds. So my delta x comes out to be 290 meters. That's how far away the thing lands. So our idea here is that we're going to use the time from the y in the x to figure out what's going on.